Welcome to Statistical Quality Control. Today, we are diving into one of the most powerful tools in manufacturing and business, the 3 Sigma control chart. Imagine driving down a highway. As long as you stay between the painted lines, you are safe. But if you drift over the line, an alarm goes off in your head. Control charts do exactly this for business processes. They create a safe lane for operations, allowing us to distinguish between normal, everyday variations and serious problems that need immediate attention. Let us explore how this works. Now that we understand the highway analogy, let us look at how it applies to data. In statistical quality control, a control chart is a visual graph used to study how a process changes over time. The term 3 sigma refers to the statistical boundaries placed on this graph. Sigma is simply the Greek letter we use to represent standard deviation, which measures how spread out or scattered your data is from the average. A 3 sigma control chart establishes a center line for the average, along with an upper and lower boundary exactly 3 standard deviations away. If data points stay inside, the process is stable. If a point falls outside, it signals an unusual event requiring immediate investigation. This brings us to an important question. Why do we specifically choose the number 3 for our boundaries? The answer lies in the mathematics of the normal distribution, the famous bell-shaped curve. According to the empirical rule of statistics, if a process follows this curve, about 68.27% of outcomes fall within one standard deviation of the mean. Moving further out, about 95.45% fall within 2 standard deviations. Finally, exactly 99.73% of all outcomes will naturally fall within 3 standard deviations. This means if the process is working perfectly, there is only a tiny 0.27% chance that a data point will randomly fall outside these limits. Knowing that only a 0.27% chance exists for a point to fall outside naturally, we can confidently assume that any point outside the 3 sigma limits is not a random accident. It means something is broken. If we used 2 sigma limits instead, about 4.55% of perfectly normal points would fall outside, causing workers to constantly stop machines for false alarms. On the other hand, if we used 4 sigma limits, the boundaries would be so wide we might miss real problems until it is too late. 3 sigma is the perfect mathematical sweet spot. Even if data is not perfectly bell-shaped, Chebyshev's inequality guarantees at least 88.8% of data falls within 3 standard deviations. Now that we understand the theory, let us look at the mathematical representation, starting with the anchor of our chart, the center line. The formula is beautifully simple. CL equals to mu. Conceptually, this line represents the historical average, or the ideal target value that the process is constantly trying to hit. In this equation, CL stands for the center line, and the Greek letter mu represents the true average of the process. This line is drawn right down the middle of our control chart. If a machine is supposed to fill bottles with exactly 500 milliliters of water, then mu would be 500. If the average increases or decreases, this center line shifts accordingly, moving the entire safe lane up or down. Building on our center line, we must now establish the ceiling of our safe operating lane, known as the upper control limit. The formula is UCL equals mu plus 3 times sigma. This formula calculates the maximum acceptable boundary for our process. UCL stands for the upper control limit. Mu is our historical average and sigma is the standard deviation. The number 3 is our chosen multiplier, based on the 99.73% statistical rule we discussed earlier. Any value above this ceiling is a statistical anomaly, telling the operator that items are too large or heavy. Notice that as the standard deviation or sigma increases, the process becomes more chaotic and the UCL moves higher up, widening the acceptable lane. Finally, to complete our safe lane, we need a flow, which is the lower control limit. The formula is LCL equals mu minus 3 times sigma. This serves as the minimum acceptable boundary. LCL stands for the lower control limit, mu is the average, and sigma is the standard deviation. Any value dropping below this flow triggers an immediate warning, indicating the process is producing items that are too small or too light. Just like the upper limit, this boundary is highly sensitive to the standard deviation. If the standard deviation decreases, meaning the process is becoming more precise and consistent, the LCL will move closer to the center line, resulting in tighter, narrower control limits. Before we move on to a concrete example, let us visualize everything we have just built. On your screen is a standard 3 sigma control chart. The horizontal axis represents the sample number over time, while the vertical axis represents the measured value. Right in the middle, you see the solid center line at mu. Above and below it are the dashed lines representing the upper and lower control limits. Notice how the blue data points bounce around harmlessly near the center line. This is normal, everyday variation. However, look at the red point that breaks through the upper control limit. This immediately catches your eye, signaling exactly where the process went wrong and when operators need to intervene. Now that we have seen the diagram, let us walk through a simple numerical example to see how these formulas work in practice. Imagine a factory produces steel rods. We are given that the historical average length of a rod is 100 centimeters and the standard deviation of the cutting process is 2 centimeters. We need to calculate our 3 control lines. First, we identify our given values. Mu is 100 and sigma is 2. The center line is simply the average, so our center line is exactly 100. Next, we set up the upper control limit by taking the average of 100 and adding 3 times the standard deviation of 2. We will perform the multiplication in the next step. Continuing with our calculation, we multiply 3 by 2 to get 6. Adding this to our average of 100 gives us a final upper control limit of 106 centimeters. Any rod longer than this triggers an alarm. Now we calculate the lower control limit. We take the average of 100 and subtract 3 times the standard deviation of 2. Multiplying 3 by 2 gives 6 and subtracting this from 100 gives us 94. Therefore, our final lower control limit is 94 centimeters. In practical terms, as long as the factory's steel rods measure anywhere between 94 and 106 centimeters, the cutting machine is working perfectly normally. Let us look at a slightly more applied scenario. A bakery produces loaves of bread with a target weight of 400 grams. The standard deviation of the baking process is 5 grams. Today, a sample loaf weighs in at 418 grams. We need to determine if the process is in control. First, we identify our mean, mu, as 400 and our standard deviation, sigma, as 5. We start by setting up the upper control limit. We take the target weight of 400 and add 3 times the standard deviation of 5. Multiplying 3 by 5 gives 15. Adding this to 400 gives us an upper control limit of 415 grams. This is the absolute ceiling for our bread weights. Moving forward, we now calculate the lower control limit to find the minimum acceptable weight. We set this up by taking the target weight of 400 grams and subtracting 3 times the standard deviation of 5 grams. Just like before, 3 multiplied by 5 is 15. This 15 grams represents the maximum allowable drop in weight. Subtracting 15 from 400 gives us a lower control limit of 385 grams. This means the acceptable, safe operating range for the bread loaves is anywhere between 385 grams and 415 grams. Any loaf outside this range is a statistical anomaly. Now we reach the final step, evaluating today's sample. The manager weighed a sample loaf at 418 grams. We compare this to our calculated boundaries. Because 418 is strictly greater than our upper control limit of 415, this data point falls outside the 3 sigma boundaries. The manager must conclude that the baking process is currently out of control. Perhaps too much dough was added or the scale is broken, but the mathematics clearly show that this is not a normal, everyday fluctuation. An immediate investigation is required to fix the process. Having seen the math in action, let us discuss why this matters so much in the real world. The 3 Sigma control chart is a foundational tool in modern manufacturing. Without it, factory workers would constantly overreact to tiny, normal variations, tweaking machines unnecessarily and actually causing more defects. Conversely, they might ignore a slow, creeping problem until thousands of defective products have already shipped. By using 3 sigma limits, companies create a clear, objective mathematical rule for exactly when to leave a process alone and exactly when to intervene. This saves millions of dollars in wasted materials and ensures that everything from car brakes to medical syringes is manufactured safely and consistently. We have covered a lot of ground today, so let us summarize the key takeaways. First, a 3 sigma control chart is a visual tool that defines the acceptable boundaries of a process using the mathematics of standard deviation. Second, by setting limits exactly 3 standard deviations above and below the average, the chart captures 99.73% of normal process variation. Finally, this mathematical framework allows businesses to easily distinguish between harmless everyday fluctuations and serious process failures. Mastering this concept is your first major step in understanding how world-class quality control is achieved. You now have the tools to analyze and stabilize real-world processes.